Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem, extra characters in a string. We're given a 0 index string S and a dictionary of words. So kind of like this is our dictionary of words and this is our string. We want to break this string up into one or more non-overlapping substrings. I think that this is worded, at least for me, kind of confusingly. Like they might as well not put non-overlapping, like just taking a string and breaking it up into substrings is pretty much exactly what they mean. Like, for example, if you have this string, Leetcode, I should probably make this Neatscode, but oh well. Like if you took this and broke it up like into this string and this string, that's perfectly valid. What we can't do is break it up into that string and then reuse another character. Like we can't have overlapping substrings. I think that's probably what they meant here. But one of the differences between this problem and another very similar problem, which is called word break, is that actually we can skip characters for this one. So we don't have to use every single character. And that's good because when you look at the words available to us here, Leetcode and Leetcode, there's no S in any of those words. So we probably won't be able to include that. And what we're trying to do here is to break this up into words in our dictionary. So this is perfectly valid, Leetcode. And notice how we had to skip one character. So that would be the result that we return. And what we're trying to do is minimize this return value. So in other words, we want to skip the fewest number of characters possible. So not super crazy, not a crazy problem to understand. And I would say that to approach this problem, it's not bad to initially think about the brute force. And if you're familiar with the word break problem, you probably know that this problem can be solved with dynamic programming. So I'm going to kind of show you how to go from the brute force to dynamic programming, but there actually is another optimization we can make from the DP solution. I'm kind of going to spoil it for you right now, but I will explain how we arrive at that solution. We're using a Trie data structure. It's not quite as complicated as you would think. It's just that we have to code up some pieces of that trie. So that solution just turns out to be a bit longer than the regular DP solution. So let's get started. And for the record, the DP solution actually will pass as well. So if you don't want to do the trie solution, you don't have to, but I think it's worth learning because it's not as confusing as you would think. So first of all, when we start at like this string, like this is the input string S, probably we're going to traverse it with some pointer I. So we start at the beginning of the string. Now, we could just check every single substring, right? Like, does this substring exist in our dictionary of words? And probably if we're going to do that, we might as well convert that list of words into a hash set because it'll be easier to make that lookup in a hash set rather than traversing the entire array of words. So that's one part of this. Now, what if this word does exist? Like, what if L is just a word in the dictionary? Well, then we would say, okay, we already know that this is a word. So now we're solving this sub problem. We're asking the same question here. What is the fewest number of characters that we can skip such that we break this up into words that belong in the dictionary? So that's one possibility. Now, the other possibility is that this is not a word in the dictionary. Okay, well, let's just try again. Let's try the first two characters. Is this a word? No, it's still not. Let's try the first three characters. It's still not a word. Let's try the first four. This actually is a word in the dictionary. So we would pretty much do what I said earlier. We know this is a word now. Now we're solving this sub problem. And we would get here at S. And of course, by looking at it, we can kind of tell pretty quickly. We're never going to be able to form a word starting at S that belongs in the dictionary. So we'll possibly try every single way, every single prefix here. That word prefix is kind of a hint at an optimization that we're going to make later on. But what you'll find is here again, none of these prefixes are a word in the dictionary. So there's actually another choice that we can make. We can choose for any particular character that we're at, let's skip this guy. So we choose to skip S, then we start at C. We'll try all of these prefixes, and then until we get to this one, code, which actually does exist here, then we will say, okay, we found this word and now we're going to try searching over here. Well, we got to the end of the string. That's probably the base case. Now, what do you think for this subproblem, an empty substring, what's the solution going to be? What's the minimum characters that are left over? Or in other words, where's the minimum characters that we have to skip? Probably 0. So that's going to be the return value from the base case. If it's not clear to you by now, the fact that we're thinking of this in terms of decisions means we're going to have a decision tree, meaning we're going to solve this problem recursively. And with this type of problem, when you solve it recursively, what you'll find is we're keeping track of a single pointer. We're keeping track of I, the position that we're at. That defines the subproblem that we're trying to solve. It is going to be possible that sometimes within our decision tree, we arrive at the exact same subproblem. For example, I equals 4 here, I equals 4 here. Why should we have to solve the same subproblem multiple times? If we have to build out the entire decision tree for this subproblem over here, why should we do it a second time over here? We probably shouldn't. We should just take the result of this subproblem, put it in a cache. I usually like to use a hash map. You can also use an array, but put it in a cache so that next time we try to solve that subproblem, we can recognize it, and then we can just look up the return value in our cache and just skip all of that repeated work. So that's the idea here. Now, if it's not clear to you that no matter what happens, we're always going to have a branch where we skip the current character, because in this case, we found that we just couldn't form a word starting at S. So then I said, okay, well, let's just try skipping the character. But it could be possible that, and let me actually draw out an example. For example, something like A, B, C, D, E, F. Let's say the words in our dictionary are A, B, C, and B, C, D, F. What you'll find is actually starting at A, we can find a word starting at A. We find ABC, right? That works. And then when we get to D, we find that, okay, we can't find any more words here. So the result of this is going to be 3. We have to skip these 3 characters. We couldn't make a word out of them. But just because we could make a word starting at A doesn't mean we have to. We should still consider the other possibility where we skip A, because if we skip A, what you find is you can use this word starting here, and that will make up all these characters. And in that case, we only have to skip a single character, so therefore the return value becomes 1. That's obviously less than 3. So no matter what, when we arrive at a character, we always want to consider the possibility that we skip that character. Now let me code up this sort of DP, aka memoization solution, and then I'll show you how we can optimize it using a trie data structure. So the first thing, like I said, is I'm going to take that dictionary of words, that array of words, and convert it into a hash set. That's going to make our lookup a little bit easier. And I'm also going to have a DP cache. Actually, I won't even write that out yet because I'll show you how we can add caching after the fact. It's pretty easy to do. I always call the recursive function DFS. You can call it something else if you want. We only need a single parameter, the current character that we're at. And so the main base case, like I said, is when we get to the last character, or we get like out of bounds. So like I is equal to the length of the string. Therefore, we return 0. So simple enough. Now, I'm going to start with the case where we skip the current character, where we say 1 plus DFS of I plus 1, because the result, remember, is going to be the total number of characters that we have to skip. And if we skip this current character, we're taking 1 and adding it to the return value of this. You might be wondering, if we weren't doing this, what would have been a good initial value to set result to? Well, since we're trying to minimize it, you could set it to infinity, but also another one actually could have just been, since I defines the current subproblem, we could just take the remaining portion of the array, aka the length of S minus I. That would have been a perfectly reasonable default value for the result. The reason we don't have to do that, though, is if we're not able to form any words at all starting from I, this like branch in our decision tree is going to actually account for that. So in a way, this might end up setting the result equal to the length of the string minus I. So that's just something I thought was worth mentioning. It's not like super important to solve this problem or anything. Now we want to get every single prefix starting at I. We want to see if any of those form a word that is contained in our dictionary. So we say J in range starting from I, going up until the end of the string. And what's the substring? Well, it's going to start at I, it's going to end at j, but this is non-inclusive in Python, so we have to say j plus 1. And what we want to know is this word in our words hash map now, or our hash set? And we can do that with a conditional. If that is the case, then we do a branch. We make a recursive step. We say, okay, let's call DFS. Now, where do you think we should start? Well, probably where this word ends, and that's going to be j plus 1. So that's what our DFS is going to do. What do we want to do with the return value? Well, we want to update the result, and we're trying to minimize the result. So we're going to set it equal to the minimum of itself and the return value of that DFS. And that's actually pretty much it. Like, that's pretty much the entire recursive solution. Once we're done with that, we just go ahead here and return the result. And outside of that, how are we going to call our DFS? Probably just by starting at the beginning of the string, passing in 0. Now, the last thing I didn't do is add caching. Well, it's pretty easy to do, like I said. Well, first we create a cache itself. I use a hash map usually. You can use an array if you want in this problem. Here, we can have a second base case, which says, if we've already solved this subproblem before, if I is in the DP hash set, then return the value that is stored there. And here, before we return the result, we should probably add to the cache. So we'll say DP of I is going to be equal to the result before we end up returning. You could also probably replace this with that, but I think just adding this line of code is a bit simpler. Now, one last little thing we can do, we can actually get rid of this base case, because this just says if I is equal to the length of s, return 0. Why not just add that to our cache? Why not just say for this key, the length of the string, it maps to 0. So if we do that, we can actually just get rid of this. Now, let's go ahead and run this to check if it works. And as you can see on the left, yes, it does. But there is an optimization we can make, and let me show you what that is. Actually, before we do that, let's understand what's actually going on here in terms of time complexity. Because how many times is this recursive function going to be called when the value has not been cached yet? Probably n times, because the number of possibilities we can pass in for I is going to be n, where n is equal to the length of the string. And within the function itself, you can see we're looping up to n times, up to the length of the string time. So the time complexity is n times n. And lastly, you can see within that loop, we're creating a substring, which is going to be up to of length n. And checking if that substring is in like a hash map, we have to hash that string under the hood that's going on at least. So if the string is of length n, then we have to add another factor of n to our solution. So the overall time complexity is obviously big O of n cubed. And the optimization that we're going to make is actually going to be from removing this if statement, because this is a prefix. And when you're checking, for example, like let's say our list of words is like leet and code and Leetcode. And if we're going through some really big string like A, B, C, D, like I'm just putting out random characters here, and we get to this character, A, we're going to check this prefix. Is it within this list of words? Nope. Then we're going to check this prefix. Then we're going to check this prefix, this prefix. We're just going to keep doing that. And that just does not seem like the most efficient way to do it. Is there not a better way where like we can just make the determination based on the prefix, like comparing this prefix to the prefix of each of these words? Is there not a data structure that can allow us to do that? Well, actually there is. It's called the prefix tree, aka the trie. Trie is just not a good word for it in my opinion. It's prefix tree is the better name because it's actually descriptive and it shows you how you can actually solve this problem efficiently. That's what we're going to do. The prefix tree, what it's going to do here is instead of just checking if this substring is in this set, we're actually going to very, very efficiently be able to compare this prefix to all of these prefixes at the same time and very quickly determine, hey, this prefix, there's no way any of these words will match it. And I won't go super in depth into what a prefix tree is. I have plenty of videos explaining that. I think my advanced algorithms course also explains it. So what I'm actually just going to do now is code up the parts of the prefix tree that we need, and then I'm going to replace this part. So it's not going to be a lot. Like we definitely don't have to code up the entire prefix tree. One thing I'm going to do here is code up the trie node, and that's pretty simple because it doesn't really take any parameters, and it's going to just have two member variables, the children, which I like to use a hash map. You can also probably use an array. I think in this problem, we're limited to like lowercase characters. So you could have an array of like size 26, but I'm not doing that. And we also want to know for every character, is it actually the ending of a word? Because we might have some prefix that matches one of the prefixes of the words, but it doesn't match the entire word. So that's kind of what we're accounting for here. This is going to be a Boolean. Initially, let's just set it to false. And now I'm going to have the actual trie class, and it's going to have a constructor. Before I actually define what the constructor is, I think it lends itself to know how we're actually going to be using this trie. Like here in this if statement, we are trying to figure out, like, does this prefix match any of the words in our trie? So to do that, we're going to go character by character. I'm going to get rid of this if statement now. What we would want to know is, does the character at position J match any of the beginning of the words that we have? So at the beginning, initially, what we're going to say is current is going to be equal to the trie root. I won't even code this up yet. I guess I'll just kind of explain it conceptually. But then for every character, we're just going to traverse the words. So before we try to do that, we should probably make sure that all of the words are inserted into the trie. So that's why in this constructor, I'm passing in the list of words. And with those words, I'm going to build the trie. We're going to have a root of this trie. It's going to be a member variable. It's going to initially just be a trie node like that. And then we're going to build the trie. We're going to go through every word in the list of words. We're going to start our current pointer at the root. And from the root, we're going to insert this current word. How do we insert a word into a trie? We go character by character because every character is corresponding to a node in the trie. So for every character, we want to create a trie node with this character. So what we would do is say self.root, the children of the root, like this, let's get its children, is this character in the children. Because if we were to try to do this, if we were to try to say for the children, add this child and do that, like let's just add this child and give it a trie node of its own. Well, what if there was already a trie node for that child? That's the case that we want to avoid. So before we do this, we say if this character is not in the root's children, and actually not the root's children. That was a typo on my part. We defined our current pointer up here for a reason. So I'm actually going to replace that with the current. And now I'm going to put the current here and make sure this is a part of the if statement. Now, if there was already a trie node there, then down here, we're going to shift our current pointer to that node just like this. And if we happen to insert one, we'll end up shifting the pointer regardless. Like this is going to execute regardless of whether the if statement does or not. And after we've gone through every character in the word, here we want to say the word, it does form a word. Basically, we're setting this to true now. So that's pretty much all we have to do for our trie, because as for actually traversing it, we're going to do that part down here. It's just going to make more sense to do it here. But now that we have that, let's see how we can actually use it. First of all, we only need to initialize this a single time. We don't need to initialize it multiple times. So I'm going to call the constructor up here. I'm going to call trie, passing in the dictionary, and we probably don't need this line up here anymore. That hash set is no longer needed. And I'm going to pass in the dictionary. I'm going to create an instance of the trie, and I actually want the root pointer of the trie. So here I'm going to write .root. So there we go. We've built our trie, and here, as we start going through every prefix, every character starting from, some position, we want to then start at the root of our trie. We're going to here say current is equal to the trie. We saved the root up here, so we can always assign our pointer to the root. And now here, for every single character, we want to know, is this character in the children of our root or whatever current pointer we're at? Is this in current.children? If it's not, if this is not the case, then that's the very simple case, because we know there's no way we're going to be able to form a word starting at J that is within our dictionary of words. There's just no way. So here we can probably just break out of this entire loop and just return. And if this does not execute, then we can, first of all, shift our current pointer. Now we're going to go to current.children of S of J, because we know that this is a child and therefore we move to it. So for the next iteration of the loop, we'll be able to continue to do these checks. We also potentially want to update our result. If we were going to update our result, we'd do it the same way. We'd call min and take the minimum of the result and the minimum of DFS of J plus 1. But we can only do this not only if this is a child of our current trie node, but if that current trie node now forms the end of a word. So if current.word, then we can make this check. We can't just do it for a prefix of a word. We have to make sure it matches an entire word in the dictionary. So that is, I think, all of the modifications that we have to make to the code. You can see that this code actually didn't change much. It was just adding some trie utilities, a trie node and the trie constructor. And also you can pretty much just by looking at it confirm that we did improve the time complexity, because there's no substring here. We're just comparing like a single character and checking if it's like the key in a hash map. There's no non-constant operations going on here anymore. So let's run this code. And of course, I always have a bug. I forgot the colon here. Let's try that again. And as you can see, now it works and it's pretty efficient. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. I added my own code editor recently. I'm really excited about that, and I'll see you soon.